In the previous chapter, uh, we expanded our definition of the derivative from just the slope, the y, change in y over change in x slope, to a more broad definition of thinking about it as the direction of the tangent line. In this chapter, we're going to expand that definition even more, and the textbook, as usual, does a very nice job of explaining the algebra or sort of the symbolic manipulation of the whole process. But it it goes through the understanding or the conceptual aspect of it rather quickly. So I wanted to take some time to talk about the conceptual uh, extension of the definition of the derivative that we're familiar with. So let's first look at our definition and see why we can't extend it so easily to our to higher dimensions. All right. So first of all, let's draw a picture to start with. We've got just some generic function, and I'm going to randomly pick a point, and through that point, I'm going to sketch the tangent line, which might look something like this. Okay, so there's our tangent line for some generic function, and the standard definition, which hopefully you all remember very well, say f prime of a is equal to the limit as h approaches 0. This is one way to formulate it, of f of a plus h minus f of a all over h. So we might think that the easiest way that we could just extend this by just saying, well, we'll make f a function of vectors, a vector function, and then we're done, right? So we have a function of vectors. So then the question then becomes, what do we mean by this, right? What is a plus h? Well, if f is a vector function, then a must be a vector. So a is a vector. So if we're going to add a plus h, well then I guess h has to be a vector too. Okay, so we add a plus h, that's no problem, no big deal. We subtract f of a, which is no problem at all, and then we divide by h. But wait a second, we just said that h was a vector. So we've got this vector. So that's kind of interesting. So how do we divide by vectors? Um, you know, maybe you could think of taking the dot product of the reciprocal or something like that, but there's no clear conception of what it means to divide by a vector. So maybe you say, okay, well, let's just divide by the length of the vector. That's sort of a natural thing. What if we just do that? Okay, and that actually, you'd think maybe that's really what we care about, is that the length of h gets small, right? We don't really care what direction it's pointing, so we think the length of h gets small, so we divide by its magnitude, and it's all done. Unfortunately, we have a problem, and the problem happens immediately here with our regular two-dimensional case. Any extension of the definition we have to higher dimensions, it would be really nice if it still fit our original definition in 2 dimensions. So so let's look at that. So the problem with this is we need to get the same direction. We need to get the same slope no matter what direction we come from. Well, if h, our vector h, is pointing to the right, then h is going to be positive, and this difference, like if we look at this example for example, or this specific picture, the slope is going to be positive, so we know that if h is positive, then f of a plus h minus f of a also has to be positive. Okay. Now, in the other direction, if h happens to go in the other direction, then h is negative. So we have here a negative on the bottom. Absolute value of negative is actually positive. But because we're going in this direction, we know that f of a plus h minus f of a has to be negative. So then we have negative over positive, which is negative. So that's the wrong slope. We get the opposite value. So this doesn't work. Putting the absolute values around h doesn't work. So that fails. But the problem is even worse, because what if we just went ahead with this definition and said, okay, fine, we'll let a be a vector, we'll let h be a vector, we'll define this as our derivative, and we'll just sort of ignore the case that there's an issue in in 2 dimensions, because we already know what 2 dimensions is anyway, so we'll just do a different one in higher dimensions. Well, this gets even worse. We're dividing by the magnitude here, but when we have f of a plus h minus f of a, this sort of gives us a direction, and that direction depends on what direction h went. So depending on what direction h goes, we're going to get a different derivative, right? The smaller, sure, it's going to get smaller and smaller, and we're going to end up with some sort of, the difference is going to get smaller and smaller, and we're going to approach the limit. We're going to get some sort of tangent vector or something like that, but the problem is that it's going to have a different direction, and the direction is going to depend completely on h. So one way to think about it is that by dividing by the magnitude, we get rid of the length of h, but we don't get rid of the direction of h, and we want all of h to be able to vanish from this equation in order for it to be meaningfully our derivative. There's also some other problems, right? And those other problems have to do with just what a derivative is to begin with. So let's say we had some surface, some function from R2 to R, right? So that's a function of x and y which maps to z, and we get this sort of surface here. What is the tangent to that? Do we mean a tangent line? If we mean a tangent line, what direction do we mean? Do we mean a line that points in this direction here? Do we mean a line that points in this direction here? What do we mean? Maybe we mean a tangent plane. But do we always mean a tangent plane? What if I switch to, what if I look at a vector field? How do we find the tangent to a vector field? What does that even mean to have a tangent to a vector field? So really, this sort of understanding as a tangent, it's very difficult to conceptualize in higher dimensions. So let's go back to our original derivative, this function over here, and think about it for a second. The good thing about derivatives, well, the thing about the tangent line is that it just sort of kisses up against the curve, right? And that's sort of a funny thing to define mathematically. That's what limits were developed for, was to define that sort of funny thing. But one way to think about it is that the derivative at this particular point, or the tangent line at this particular point, is the best linear approximation to the curve at that point. If I zoomed in on this area right here, we would see that the tangent line is obviously linear, and the function itself is actually pretty linear in that respect because we zoom in. And the further and further we zoom in, the more and more linear our function looks, and the better our tangent line is an approximation to it. So what if we thought of the tangent line as the best linear approximation to the curve? How would that change our definition of the derivative? So let me get rid of this for a second here, and we will sort of start over. Okay, so here let's do this in the standard 2 dimensions. Okay, I could write my tangent line as y minus f of a is equal to m times x minus a. To solve for y, I can get that y is equal to m times x minus a plus f of a. Okay, so what does it mean to be a good linear approximation? Well, one way to think about what it means to be a good linear approximation is, again, if I'm in this area here, that the difference between my function and the tangent line is pretty small. So we can look at it like that. So let's look actually at the difference between the function f of x and the tangent line. And we're going to move over some little bit h, because obviously we know at the point the difference is 0. They intersect. So we don't want to look there. We want to move over a little bit. And we're going to say, if we move over a little bit, they still should be pretty close, because the tangent line is a good approximation for the function. So we have, we want to do f of a plus h, and then we want to subtract off y to look at the difference at the tangent line. Now, we have to be careful. Y, we're doing y not at x or at a, we're doing y at the point f of a plus h. So what does that simplify to? So we're going to plug in, so this difference is equal to f of a plus h, great, minus y, which is m times, and now remember we're plugging in a plus h for x, a plus h minus a, and then I'm also subtracting off f of a, right, because I'm subtracting off all of y. So I subtract off this term, and I subtract off this term, and in for x, I plugged in a plus h. Okay? Okay, so let's simplify this a little bit. So we get that the difference, so let's call this the difference, so I'm just going to call it difference, is f of a plus h minus the a's cancel, so mh minus f of a, and we can rearrange this, f of a minus mh. Okay, so this is interesting. This is our standard difference. This is the change in y. You know, I start at a and I go to h, so here's my change in y. Okay, and now what's this guy? This guy right here is the same thing, but it's the same thing in terms of the tangent line. So I go over h. How far up do I go? Well, I go up mh. Right. So this is the change in y with respect to the function, and this is the change in y with respect to the linear approximation. All right. So ideally, if m is the derivative, and that's the question here, if m is the derivative, which, you know, that's what we want it to be, so that's what we're working on, then this difference here, this difference that we're talking about here, should be very small, and in particular, the smaller h gets, the smaller it gets. Okay. So if we look at this, what happens as h gets smaller, we get f of a basically minus f of a, so that gets closer to 0, and then h gets closer to 0, so we get m times h at 0. So awesome. So this is one way to think about our derivative, except there's a problem here. What happens if the slope here, what happens if the derivative is 2 and I plug in instead 7, right? Well, this term still goes to 0, and then h still goes to 0, so 0 times 7 is 0. What if I plugged in 5? Well, 5 times 0 is still 0. So this is actually what this is telling us. This is telling us, sort of uninterestingly, that if I take any line, any linear function that goes through this point, as h gets smaller, it gets closer to the function. So this isn't really a good way to define our derivative. So what we really want is we want the ratio. We want the ratio of the change in y for the linear function to the change in x for the other function to be the ratio to get closer and closer to 0 as well. We want that to get closer faster than anything else. So we want it to be the best linear approximation. Certainly any function through here is a linear approximation. They're all terrible, though, except for the derivative. So the way we're going to measure that is we're just going to take the whole thing here, and we are going to take the whole thing, and we're just going to divide it by h. Okay? So now we have our difference. We move over a little bit in h, and we see how much the y value changed. And we say, we do the same thing for our linear approximation, and we see how much that changed. So we see how different the y values are, and then we divide it. We find the ratio of that to how far over we moved. And if that ratio goes to 0, then we have something interesting going on here. And the reason that we do is because if this ratio goes to 0, then if I distributed this, the h's would cancel, right? And I would be left with just m. So I have to have this difference divided by h minus m has to go to 0. And that's the derivative. That's it for this video, but we'll pick up right here in the next one.